All right, guys, in this video, we're going to be going over some gas laws material. So we're getting into our Unit 7, and the main things we're discussing are kinetic molecular theory, which we reviewed back in Unit 2. So we should have some understanding of what temperature measures and phase changes, the idea of something being endothermic or exothermic and all that stuff. Now we're going to be moving on to the gas laws and then some actual calculations of for energy calculations, like how much energy is required to melt this much ice or how much energy is required to vaporize this much liquid water and things like that. But a lot of those questions can be kind of answered using dimensional analysis. And for the gas laws questions, um, it's pretty easy. You just have to remember a few things about the gas laws. So we discussed gas laws last class. Just showed you the equations, discussed the relationships and that kind of thing. And now we're just going to do some more practice with it. So the main ones we're going to be looking at today, right? If we look at your gas laws handout, right? We have all the different gas laws like, Boyle's law, Charles' law, Gay-Lussac's law, the combined gas law, there's Dalton's law, there's Graham's law, and the ideal gas law. Now, the ones we're looking at in this warm-up are, we're going to talk about the ideal gas law, so PV equals nRT, okay, all that stuff. And really what we're going to do is look at these four gas laws, but really the only one you need to know is the combined gas law. You need to know this one. And if you know this one, then you know these three, right? So the combined gas law is the combination of these three gas laws. Sometimes it's called the proportional gas laws. These equations, just these, are saying, okay, if I change the temperature, what happens to the pressure? If I change the volume, what happens to the temperature, or vice versa? Or if I change the volume, what happens to the pressure? And so really, you don't really need to know the names of the laws. Like, you don't need to know that P1 times V1 equals P2 times V2. You don't need to know that that's Boyle's law. But what you need to understand is the relationship it describes. Okay? You don't need to know that this one's called Charles' law, but you need to know that it's initial volume over initial temperature equals final volume over final temperature. But when it's pressure and volume, it's initial times initial equals final times final. And the different relationship that has, okay? So understand, if you know this gas law, if you're told that temperature is held constant, then you get rid of temperature in this equation, and what are you left with? You're left with Boyle's law, right? So what this gas law is explaining is explaining the relationship between pressure and volume, assuming that temperature is constant. This one is showing the relationship between volume and temperature, but in this case, pressure has to be held constant. This one is showing the relationship between pressure and temperature, but in this one, volume has to be held constant. Okay, so that's right. I don't need volume if it's being held constant. I don't need temperature if it's being held constant. Now, the other thing that's being held constant in all four of these gas laws, so Boyle's law, Charles' law, Gay-Lussac's law, the combined gas law, the one thing that's being held constant in all of these is the moles of gas, the N value, the number of gas particles measured in moles, right? So if we skip down to the ideal gas law, notice in this one we have N, and N means moles of gas. So, right? So in these, moles is being held constant in all of them. The only thing being held constant in this one is moles of gas. So what's being held constant in here? Volume, because it's not included, and moles of gas. What's being held constant here? Pressure, because it's being held constant, and then also moles of gas. So notice pressure and moles are not in this equation. Volume and moles aren't in this equation. So when it's held constant, you don't need it in the equation, okay? So let's look at the warm-up, okay? So the one thing you won't be given is how to convert Celsius to Kelvin. And the one thing you need to understand is it doesn't matter if it's this gas law or this gas law or any combination. Anytime you plug in a temperature value, it's got to be on the Kelvin scale. It cannot be on the Celsius scale. So if you're given Celsius, what do? You add 273 to that number, and that's the Kelvin number, and that's what you plug in for temperature. So that's kind of a little reminder here. Okay. So you need to remember this equation, and remember that's the one you need to remember, because if you remember that one, you got the three others. If pressure is held constant, get rid of pressure, and that's the equation that you use. Okay. And then you got to remember this equation. Okay. Now, in the ideal gas law, the R value is a constant, and you don't have to memorize the R values. The R values will be given to you. The main thing is you got to know which one to use. Like, so the real easy way is if your R value has atmospheres for pressure, then you're going to use this R value, right? If your question has millimeters of mercury or torr, which are the same unit, then you would use this R value. Okay. So it's just a number, and which number do you plug in? It really depends on what unit of pressure you have here. If you have atmospheres, then it's this R value. If you have millimeters of mercury for pressure, then it's this R value. Okay. All right. So the first thing is just understand the relationship, so you understand, what the expected outcome of the question is, right? So we got to remember pressure and volume have an inverse relationship. Pressure and temperature have a direct relationship. Volume and temperature have a direct relationship. And volume and moles, amount of gas and volume, direct relationship, right? The more gas you have, the more space it's going to occupy, right? So that's a direct relationship. So if we look at the answers, right, Boyle's law, pressure and volume, that's an inverse relationship. Gay-Lussac's law, pressure and temperature, that's showing a direct relationship. So if we increase the temperature, the pressure will go up, right? Volume and temperature, if we increase the temperature, the volume will go up, okay? And volume and moles of gas. If we have more gas particles, they'll occupy a bigger volume, so another direct relationship. So remember, the only inverse relationship is the pressure and volume one. And so that means if pressure goes up, volume goes down, or if volume goes up, pressure goes down, right? That's what inverse means, okay? So let's look at number one. And the first thing to do is, like, which equation should I use? So notice they say constant temperature, okay? So they give us initial pressure, initial volume. They give us a final volume. They want us to find the new pressure. So we're changing the volume. How is that going to change the pressure? As long as temperature remains constant. The other thing that wasn't mentioned, but we didn't say, we changed the number of helium particles that we had. So moles is staying constant too. So if temperature and moles are being constant, this is the equation you use. Now, you don't need to know that that's called Boyle's law, but you cover up temperature here and you use this equation. So we plug in our initial pressure, our initial volume. We plug in our final volume, which was 10 liters, and we solve for P2. P2 comes out to be 2 atmospheres. But what you should understand is, so that's our final answer. But, what was the relationship? Well, we know this is an inverse relationship. What happened to the volume? Volume increased. It went from 5 liters to 10 liters. So we know the pressure should decrease. And then here's the other deal. If we notice that volume was doubled, then that means the pressure is just going to cut in half. So we could probably just do it in our head without setting up the equation, but it comes out to be 2 atmospheres. And then, check yourself. The volume went up, so the pressure should go down. Is that what happened to the pressure? This was the initial pressure. This was the final pressure. The pressure did go down. So, our answer matches the relationship, right? If I got a number greater than 4 here, I probably mixed up my numbers when I plugged in, maybe I said the final volume was the initial volume and vice versa, right? So you got to watch out for that, right? Okay. So if we go to number 3, okay. Here we have a sample of oxygen gas in a flexible container. Understand what that would mean. That would mean that the volume's going to change. So volume's in play, right? And so the pressure is going to remain constant. So we don't need pressure in our equation. Volume and temperature are changing. So we need the equation with volume and temperature. The other thing that's being held constant, it's not mentioned, but we can kind of infer that it's held constant, is we're not changing the number of oxygen particles. So we need an equation with volume and temperature. Okay, so again, if we go to our combined gas law and we get rid of pressure, then the equation we use is V1 over T1 equals V2 over T2, right? So this is the gas law we're showing. Now let's understand this is a direct relationship, whereas this is an inverse relationship. So we have a direct relationship here. So what happened to the temperature? The temperature went from 25 degrees Celsius to 50 degrees Celsius. So the temperature increased. So the volume should also increase. So our V2, that's what we're solving for in this question, should be higher than V1. So our V1 was 500 milliliters. Our V2 needs to be higher than that. Now, this is where we got to be careful. The temperature doubled. And if the temperature doubles and volume and temperature have a direct relationship, the volume should double. So a lot of students are going to think the answer should be 1,000 milliliters because the volume should double. But this is where we got to remember, right? It's the Kelvin scale that we're comparing the temperature to, not the Celsius scale. So it doubled on the Celsius scale, but if I convert this to Celsius and I convert that to Celsius, the temperature increased, but it didn't double, right? So remember, when we plug in our temperature values, we got to plug in the Kelvin scale. So the temperature went up, but the temperature didn't double on the Kelvin scale. So the volume is going to go up. It's just not going to double, okay? It's just going to be higher than 500 milliliters. So we plug in our V1, we plug in our T1, which is 25 plus 273. That's where 298 came from. We are solving for V2, and we plug in our T2. Now, how are we going to solve for V2? It's pretty easy, right? It's going to be 500 times 323, and then we'll end up dividing by 298. So this times this divided by this will be our answer for V2, and it will be the same units as our V1. So since we plugged in milliliters for V1, our units are going to be milliliters for V1. Okay, so did the volume increase? Yes, and that's what we were expecting because a volume and temperature have a direct relationship. The temperature went up, the volume went up, but this is where we got to be careful. We got to look at the Kelvin scale, not the Celsius scale. So the temperature didn't double on the absolute temperature scale. It doubled on the Celsius scale, but that's not the same thing as doubling on the Kelvin scale. So you got to be careful. All right. So real quick for question number 4. I said you had a balloon. We needed it for the pressure to remain to change. We can't have a flexible container, so it's got to be a rigid container. So change that to rigid container, meaning volume is held constant. Okay, so we don't need volume, we don't need moles, we need pressure and temperature, right? Okay, so if we go up here, we need pressure and temperature, so we don't need volume because volume is going to be held constant because we're going to say rigid container. So again, not a balloon. All right. So we need P1 over T1 equals P2 over T2, right? So remember that is direct relationship. The temperature is going up. It's going from 298 Kelvin to 500 Kelvin. Okay. So the pressure should also increase. The initial pressure is 785 millimeters of mercury. So our new pressure should be higher than that, right? We plug in P1, we plug in T1, P2 is what we're solving for. We plug in T2. And again, we're solving for P2, kind of like how we solved for V2 up here. So what are we going to do? We're going to take 785, we're going to multiply that by 500, and then we're going to divide that by 298, and that will give us our P2. And when we do that, our P2 comes out to be 1320, and it would have the same units as our P1, which was millimeters of mercury. Okay? All right. So now we go into number 5. Okay. And here we have a balloon. So that means the volume is variable, right? Pressure inside the balloon increases. It's going to expand until it equalizes with the atmosphere again. So what's staying constant? Pressure. The balloon's just going to maintain the pressure of the atmosphere. So, so pressure's not being held constant, but the pressure in the side, but the balloon is flexible, so volume can change. Pressure's changing in this one, temperature's changing in this one. So we got pressure changing, we got temperature changing, we got volume changing. The only thing that's being held constant is moles. So we need the gas law that has everything but moles in it. So this is when we need the combined gas law. So we need all of this. Okay. And so this is where we got to be careful because that means if we're using this equation in a practice problem, understand we're going to be given 5 measurements, right? And we're going to solve for the 6th. So we have 6 things in here. We're going to be given 5 of them, and we're going to solve for the 6th one. And we got to make sure we plug them in the right spot. So we got to make sure we can interpret what our initial conditions are versus what our final conditions are, so we know which thing we're solving for, right? So we read the question. We have an initial pressure, initial volume, and initial temperature. It's just not in Kelvin, so we're going to have to switch that to Kelvin. But this would be P1, this would be V1, this would be T1 if we add 273 to it, right? So this means this is P2, and this would be T2. So the one thing we're not given is V2. We're solving for V2. And that's what they ask. What will the volume be? So what's the new volume? So V2 is what we're solving for, right? All right. So we got our combined gas law, all right? P1 was 1 atmosphere. V1 was 5 liters. T1 was 298 Kelvin. P2 was 0.5. V2 is our unknown. And T2, again, we had to add 50 to 273, and that's how we got our T2, okay? So now we're solving for this. So what are we going to do? We're going to do 1 times 5 times 323, and then we're going to divide that by 0.5, and then we're also going to divide by 298, and that will give us our V2. Now understand what we did here, right? The pressure went down, and pressure and volume have an inverse relationship. So decreasing the pressure should make the volume go up, okay? And what else did we do? We also increased the temperature, right? We sped up the particles. So if the particles move faster, that should also increase the volume. So we did 2 things to increase the volume, because volume and temperature have a direct relationship, and we increase the temperature, so volume should go up. And pressure and volume have an inverse relationship, and we decrease the pressure. So that's another driving force to increase the volume of the balloon, right? So when we solve, we got 10.8. The initial volume was 5 liters, so our new volume is 10.8. So it agrees with the relationship, okay, of both of them. So we're good to go there. All right. Okay. So those are kind of examples of gas law questions where you would use the combined gas law or any of the smaller gas laws that make the combined gas law. So P1 V1 equals P2 V2, or V1 over T1 equals V2 over T2, or P1 over T1 equals P2 over T2. So those are those types of questions, right? Now, when are we going to use this guy? When are we going to use the, whoops, that's not what I meant to do. When are we going to use the ideal gas law? Okay. Well, notice here, right, there's only one place to plug in pressure. There's only one place to plug in volume. There's only one place to plug in moles. There's only one place to plug in temperature. We're not given an initial temperature and a final temperature. We're not given an initial amount of gas and a final amount of gas. We're not given an initial volume and a final volume, or initial pressure and a final pressure. So it's not that kind of question we're going to answer, right? Understand what the ideal gas law is. And remember, we always know what R is. R is not a variable, right? So the ideal gas law is just an equation you can use that if you know the pressure, volume, and temperature, you could use this to calculate how many moles you have, right? So if you know three of the 4 gas measurements, you could calculate the 4th, right? So if I know the volume of the container, if I know the moles of gas, and I know the temperature, I can use this equation to estimate what the pressure of the tank should be with that amount of gas, with that volume, at this temperature, right? So I know 3 of the 4 variables of gas, which is pressure, volume, temperature, moles. I know 3 of them. I need to solve for the 4th one. That's when I use the ideal gas law, okay? And the trick is making sure you use the correct R value. So notice the R value tells you what all your units need to be. So if I'm using this R value, then pressure has to be atmospheres, volume has to be liters, amount of gas has to be moles, and temperature has to be Kelvin. The only difference for this R value is the unit of pressure. So notice the volume is liters, the amount of gas is moles, the temperature is Kelvin, just like this R value. The only difference is the pressure unit. So if I'm using millimeters of mercury, I'm going to be using this R value. If I'm using atmospheres, I'm going to be using this R value. If I'm solving for P, if I use this R value, it's going to come out to be atmospheres. If I'm solving for P, but I use this R value instead, the answer is going to come out to be in millimeters of mercury. Okay. So when we look at the back of the warm up, right, it's asking for the amount of gas, but grams of oxygen. We have the tank is 50 liters, so we have the volume. The pressure is 1 atmosphere, and the temperature is 298 Kelvin. So, right, remember, just last unit, if we were given the volume of a gas, we would divide by 22.4, and that would give us moles, and then we would multiply by the molar mass, and that would give us grams. But we can't use 22.4 because, why can't we use it? Because we're not at standard temperature and pressure. We are at standard pressure, 1 atmosphere. But remember, standard temperature for gases is 273 Kelvin, not 298. So we're not at standard temperature. Remember, you can only use that 22.4 liters per mole if you're at STP. We're not at STP. So what do we do when we're not at STP? Right? What do? We use the ideal gas law. Okay. So what are we going to do? We're going to use PV equals nRT, but we're going to solve for N. We're going to solve for moles of oxygen. And then once we have moles of oxygen, we know how to convert from moles of something to grams of something. We just multiply by the molar mass. So that's all we have to do for this one. Okay. So I'm using Pivner, right? But I'm solving for N. So N would be equal to P times V, pressure times volume, over R times T. The pressure was 1 atmospheres. The volume was 50 liters. The R value I'm going to use is 0.08206. Why? Because my pressure was in atmospheres. And 298 Kelvin for my temperature. So that's going to give me moles. And remember, it's moles of this gas, O2. So how do I convert to grams? I multiply by the molar mass of that gas, which is 32 grams per mole. And I get my grams. Okay. So now, hey, we got stoichiometry, a stoichiometry question, but we're not at STP. Well, if we're not at STP, that just means ideal gas law. But step 1's done for us, right? So this is step 1, right? How do I know it's stoichiometry? They give me an amount of CO2. They ask about mass of propane. So I'm going to follow my steps. Step 1, know my recipe. Well, step 1's done for me. Step 2, take the given amount and convert it to moles. Well, what was the given amount? 3.5 liters of CO2 gas at this pressure and this temperature. Well, usually when I'm given volume of a gas, I divide by 22.4 to convert it to moles. But I can't use 22.4 because I'm not at standard temperature and pressure. So I got to use the ideal gas law. So step 2, take what I'm given, convert it to moles. There's not a quick number to divide by. I got to use the ideal gas law to convert it to moles. But once I have moles of CO2, then I'll multiply by the mole ratio 1/3, and that would give me moles of propane. And then once I have moles of propane times the molar mass of propane would give me grams of propane, right? Excuse me. So again, step 1's already done for you, right? We got the balanced equation of the combustion of propane, right? Step 2, we can't use 22.4 because we're not at STP. So what do? The same thing we did back up in this practice problem. We're using Pivner. We have the volume, we have the pressure, we have the temperature, so we can solve for N, moles, right? So N equals PV over RT. We have our pressure, 1.55 atmospheres. We have our volume, 3.5 liters. Our R value is the same one from the previous question because our pressure was atmospheres, and we have 298 Kelvin. So we end up with 0.222 moles of CO2, but we're not done yet, right? So the question is, how much propane is required to burn to make this much CO2? Once we have moles, now we can use our mole ratio times 1/3, 1 mole of propane for every 3 moles of CO2. That'll cancel out moles of CO2 and give me moles of propane. And then 44.11 grams per mole, that's the molar mass of propane. So we would multiply by the molar mass propane, and that would give us how many grams. So if we burn 3.26 grams of propane, and we collect the CO2, and we collect it at this pressure and that temperature, this is the volume of CO2 we should produce, right? So, right, stoichiometry, not at STP. Sometimes you got to use the ideal gas law. But you're not using the ideal gas law for the stoichiometric step. It's just another way. If you're given volume of a gas, but you're not at STP, you got to use the ideal gas law to figure out how many moles you have. Okay. So that will do it. If you want to see number 8, just check with the key. All right.